All right, guys, now we're getting into chapter 6, which deals with integration. In chapter 6, section 1, antiderivatives and indefinite integration is what we're going to talk about. So we have several objectives here to cover. We want to write the general solution of a differential equation, use indefinite integral notation for antiderivatives, use basic integration rules to find antiderivatives, and find a particular solution of a differential equation. So we got a lot to cover, but we will explain all of this. So let's start with antiderivatives. Suppose you were asked to find a function capital F, that's important, whose derivative is lowercase f of x equals 3x squared. From your knowledge of derivatives, you'd probably say that capital F equals x cubed because the derivative of x cubed is 3x squared. That function capital F is called an antiderivative of f because you're kind of like going backwards. Antiderivative problems, it's like they give you the answer of what happens when you differentiate it, and they want to say, well, what is the original function that you should have started with? Okay, so the definition of an antiderivative is a function f is an antiderivative of little f on an interval I if capital F prime is equal to little f for all x in the interval. So capital F is called an antiderivative of f rather than the antiderivative of f because a function can have many different antiderivatives. Here's why. Suppose you had x cubed, the derivative is 3x squared. Suppose you had x cubed minus 5, the derivative is 3x squared. Suppose you had x cubed plus 97, the derivative is still 3x squared because in this case there's no constant, and but these two cases the constant's derivative is 0. So in fact, for any constant c, the function capital F equals x cubed plus c is an antiderivative of f. Okay? So if f is an antiderivative of little f on an interval I, then g is an antiderivative of little f on the interval I if and only if g is of the form g of x equals capital F of x plus c for all x and I. In other words, any antiderivative of a function, any two antiderivatives will only be different with respect to their constant. Like you can add or subtract something from one function to the other one to get the same antiderivative. Okay? So, like, if capital F of x is x cubed plus 2, and little g of x, or capital G of x, it should have been cubed, is x cubed minus 6, well, those are the same antiderivatives up to the fact that they have a different constant. So g is just 8 less than f. Just subtract 8 from capital F, you would get g. Okay, I hope that wasn't too confusing. So for example, if you know that the derivative of x squared is 2x, you can represent the family of all antiderivatives of f by capital G equals x squared plus c, where c is a constant. That constant is very important, and you have to put it there on all your antiderivatives. It's known as the constant of integration. The family of functions represented by capital G is the general antiderivative because in general it's going to be x squared plus some constant. We don't know what the constant is, so we just call it the general constant. It could be a positive number, it could be a negative number, it could be a fraction, decimal. You don't really going to get percents. It could be an irrational number, whatever, or it could be 0. That is called the general solution of the differential equation. So the differential equation is an equation given as a derivative. A differential equation in x and y is an equation that involves x, y, and the derivatives of y. So for example, y prime equals 3x and y prime equals x squared plus 1 are examples of differential equations. So let's find the general solution of the differential equation y prime equals 2. So to start off, you need to find a function whose derivative is 2. One of those functions would be y equals 2x. Now you can use that theorem to conclude that the general solution of the differential equation is y equals 2x plus c, because in general the antiderivative of 2 is going to be 2x plus some constant. So here we just have a picture of several of the different graphs of y equals 2x plus c for different values of c. The one that goes through the origin would be if c is 0, this one is if c is -1, and this one is if c is 2. Notice they're all the same graph. They're just shifted up or down c units. But each graph is going to have the same slope at each point with respect to each x value. So if I go here, here, or down here at the y-intercept, you're going to have the same slope at those points because the derivatives of all three of these equations is going to be just 2. So let's talk about some notations for antiderivatives. When solving a differential equation in the form dy dx equals f of x, it's convenient to write it in its differential form, like dy equals f of x dx. The operation of finding all solutions of this equation is called antidifferentiation or indefinite integration. And it's notated by the integral sign, which is like an elongated S. So the general solution is denoted by, you would read this, y equals the integral or the antiderivative of f of x dx, and that equals the capital F of x, which represents the antiderivative of f plus c. The expression here is read as the antiderivative of f of x with respect to x, or the integral of f of x with respect to x. So the differential dx serves to identify x as the variable of integration. The term indefinite integral is a synonym for antiderivative. Also, if I was doing integral of 2x dx, when you write the answer, the integral and the dx kind of serve as grouping symbols around the 2x, and that is what you're anti-differentiating. So when you perform the, quote, operation of anti-differentiation and you get x squared plus c, the integral symbol and the dx kind of go away. Just like when you take the square root of 4 and you get 2, you don't keep writing the square root symbol because you performed the operation of taking the square root. Okay? All right, guys, that's it for this video. Next one, we're going to talk about some integration rules.